Okay, so what this internal plane of symmetry suggests is that these groups are the same. And in fact, they are. So what I'm circling, these are the two other substituents bound at that position, at that carbon. So now I'll redraw this because now that looks busy. But what you're comparing is all of the substituents to that carbon. So right away, we have a CH3 and a hydrogen. Those are clearly different. So that's two different groups. Now it's a matter of determining, are the rest of these different? So if we compare this carbon to this carbon, that's what's bound to our center that we're interested in, the chiral center. Those are both CH2s. So far, those are the same. Then you have to continue moving. So now we compare this carbon to this carbon. Those are both CH2s again, bound to another carbon. So once you check that next spot, you're back to, you're at the same point now, regardless if you went left or right. So what that's telling you is that these are identical groups. So basically, if you were to define the substituents to this carbon, so define the groups, we'll say, you would have a CH3, a hydrogen, and then two CH2, CH2, CH2 groups. And then you get to the other side. So I'll stop with that. But it's the CH2, CH2, CH2. That's what I mean by this. And it's identical on either side of the carbon. So that's why the answer to that homework question, I think it was how many different substituents are there in methyl cyclohexane? The answer is only 3, because the two that are bound to the ring are the same. So those aren't different. So therefore, this would be a chiral molecule. That center would not have R or S, which means that you don't have to indicate if it's a wedge or a dash. You just have to make sure the methyl group is there. So like this is equally accurate if you just leave it kind of like planar, like this. So questions on that? I think that's a good molecule to start with. You can compare this idea briefly to something like this. This is achiral, but it might be more obvious because you have two methyl groups that are the same. That's like the same argument as the two hydrogens. These are the same groups, so therefore they can't be chiral, which is the same idea as this group being the same as this group in the cyclic structure, even though it's a little bit harder to recognize. So questions on any of that? Otherwise, I'll jump into maybe more questions, more difficult questions. All right, hopefully that's making sense. Now, yesterday, a great question was asked in class in recitation. It was like, what happens if you add a double bond? And I think this was a great example to determine R and S and show how this stuff is extremely nuanced. So let's look at if you add the double bond now. So it depends on where the double bond is for if it'll matter. So put it here and then here. Okay. So if we were to consider this one, this is achiral, just like the last molecule, but for a different reason, because this carbon, the same one that we were interested in, is now bound only to 3 groups because this double bond removes the implied hydrogen. So there's only 3 groups, so this can't be a chiral center from that definition. However, if you put the double bond here, this is now a chiral center because you broke the symmetry. The double bond is no longer, it breaks the symmetry. This is no longer the same group down here as up here. So now you have to determine, is this R or S? You have to determine the absolute configuration, which the reason this is a good example is it's not trivial to tell the difference between this group and this group. You have to go through it systematically and use the Cahn-Ingold-Prelog rules to convince yourself which one is which. So let's do that. Okay, so if we're looking at the carbons that are the substituents to this carbon, we have a methyl, right? We have a hydrogen that's in the back, and then a carbon double bound to another carbon, and then there's a hydrogen there, and a CH2 bound to another carbon. So right away, in the Cahn-Ingold-Prelog rules, what you're interested in is the atomic number, right? The highest atomic number is the higher priority. So here we have carbon, 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 and a hydrogen. So our hydrogen is definitely our lowest priority. So I'll draw it in and just call this 4 for lowest priority. Now you have to compare the carbons. They're all the same, but we know these groups aren't the same. They're not identical, even though the first atom is identical. You have to then continue. So this carbon is bound to 3 hydrogens. This carbon is bound to 2 carbons. In the Cahn-Ingold-Prelog rules, you consider a double bond as 2 different bonds for this counting idea. So what I mean is you consider this carbon bound to 2 carbons, where you would consider this carbon only bound to 1, because you ignore the chiral center, right? Because the question is what is bound to the chiral center, so we don't consider it in this counting idea. So here we have a carbon bound to 2 carbons and a hydrogen. Here we have a carbon bound to 2 hydrogens and another carbon. So this is the highest priority down because we have an additional carbon that's bound at that center. So there is this additive idea in the Cahn-Ingold-Prelog rules if the atoms are the same. So here they're all carbons. So the one that has 2 carbons down there is considered higher priority than the one that just has 1. Okay, so hopefully this makes sense. I tried to go slow and deliberate through my thought process, but this is a very difficult thing, which is I think why this is a good example, because it's not trivial to determine what's the difference here in priority. So now I'll redraw this once more. Now that we're convinced this is the correct order. So here is group 1, here's group 2, here's group 3. Now you have to determine which direction this is going from highest priority to lowest. So this looks like it's going clockwise, so the R direction. So it looks like R. The reason I go through this like this is because you always have to check where the lowest priority is. If the lowest priority is in the back, then the chirality is always what it looks like. The absolute configuration is what it looks like. If the hydrogen is not in the back, so if it's a wedge, then it's the opposite. So here, because the hydrogen is a dash, this is R. The answer is R. So once more, this is R. Because the hydrogen is in the back. The reason we know the hydrogen is in the back is you can only have 1 dash in 1 wedge. We see the wedge with our methyl group, so the hydrogen has to be a dash, so we have that. And I missed the double bond there. So you were probably very confused because it wouldn't be chiral, but the double bond that was needed to be there. Highest priority gets 3rd carbon. I don't really understand your question, Ben. So the highest priority is the position that has the highest atomic number to that spot. So here we have a carbon and a carbon, so those are the same. So there's no priority difference there. But if you continue, this carbon is bound to 2 more carbons, whereas this carbon is only bound to 1. So the fact that this is bound to an additional carbon, this group down here, is why it gets the highest priority.
So then would it be wrong to just, like, if you're following down the whole length of the substituent, and then HH, and then you just compare the C and the H? So if you go like CH, C for the double bond, and then CHH, if you're just following like the written out formula, or do you have to know that it's bound to 2 carbons and that's what makes it higher priority?
So my internet cut out halfway through, but I think I'm following. So let me recap what I heard, and then I think I can answer, but we might have to go through it again. But so you're saying if you compare this position to this position, just written out formula, so like this one here, would be a CH2, CH2, what I've circled, and this would be a CH and then bound to another CH, and this is bound to another thing, right?
Yeah. Mm-hmm.
That's what you're saying?
Yeah.
So yeah, you can do that. If this is easier for you, then you can tell that this is the higher priority for the same reason, because this carbon is bound twice. And I say like air quotes twice because it's only bound to one carbon. But in these rules, we say that the double bond counts as if it's bound to two, just for the sake of determining priority. Does that make sense?
Yeah, thank you.
Yep. Yeah, because like, let's say you had, well, this will be a bad example because of this is also chiral, but my point is this spot going down here would be higher priority for the same reason that the double bond is, because you have the additional bond to the carbon. In this case, you actually have another carbon. In this case, you had a double bond. So the priority of these two groups would be the same so far. Like if you were considering this at this center, here you're bound twice to a carbon, here you're bound to two different carbons, those would be the same in terms of priority. You would have to then go to the next carbon. And then when you go to the next carbon, you'd see that this is bound to two carbons and then the third carbon here by our bond counting, and this is only bound to one. So then this would be the higher priority now in what I've drawn. So hopefully that example further clarifies. Okay, any other questions? Otherwise, I'll move into other stuff. Okay, so we determined absolute configuration. So let's just jump into stereoisomeric relationships, because you continue with the idea of absolute configuration, and then we'll finish with the Lewis acid-base stuff. So first of all, let's define the relationships. There's two that you're going to be responsible for at this point, and one is enantiomer and the other is diastereomer. So an enantiomer is, again, these are relationships. So that implies that there's at least two molecules that you're comparing, and you're describing the relationship between these molecules. So when you're doing that, an enantiomer has all chiral centers opposite absolute configuration. So everywhere you look in textbooks you read and other resources will tell you that they're mirror images, which is completely correct. That's what they are. But that is usually worthless for solving the problem. What is helpful for solving the problem, because they usually don't draw it like it looks like a mirror image, because then that would be really easy to just determine fast. They want to make the questions more difficult. So by doing that, they don't make them look like mirror images. So the only way you can tell that they're mirror images is if you determine the absolute configuration at all the chiral centers, and then if they're opposite, so like if one molecule was RR, is where you, by definition, you have to have two or more chiral centers. And only one, well, not all of the chiral centers are different. At least one, but not all. And that's key. Our opposite configuration, like the same thing that we talked about with enantiomers. So an example of this would be like RS, it's one diastereomer would be RR, where you changed the S to R, for example. That would be a diastereomer. Okay. So those are the definitions. Now let's apply it to a question. So let's see, what can I come up with? Let's do a Fisher production, since we already did our skeletal stuff here. And then I will compare this to skeletal to make this more instructive. Okay, so first thing to mention is why is this just a line? And it's because this is achiral. Like, why isn't this a dash or a wedge? It's because there's two hydrogens there, so that position is achiral. This position is the same as this one. And by the way, these molecules are the same except for their stereochemistry. Their stereochemistry may be different. And looking at it, I don't know if they're different or not because I just made it up. We'll have to do it to determine. But they're not isomers in terms of like structural isomers. They're all the same bonding because here's carbon 1, here's carbon 1, 2, 3, 4, here's 2, 3, 4. So at 1, we have our CHO group. At 2, we have the bromine. At 3, we have chlorine. And at 4, we have our 2 hydrogens in the OH. Now, I should have mentioned this first, but CHO is an aldehyde. It is this group. It's not an alcohol like this because that would be COH. I think I might have mentioned this in a previous recitation. It's hard to remember what I've said in the different recitations, but anyway, just to be complete, CHO refers to the carbon double bound to oxygen and 1 hydrogen there as well. So it's the aldehyde group. Now, let's determine what centers are chiral. So this position has a CHO group, a bromine, a hydrogen, and then this whole thing. The whole thing at the bottom is clearly different than the CHO. So this position is chiral. And that's this position. Both of those are chiral. And then this position is a chlorine. And then this whole group, which is different than the CH2OH. So this is chiral as well. And this is chiral as well. Notice I didn't check it on the other group, like the other molecule, because we did it on one, so they're the same. So it's not, you don't need to spend the time to check on that one. Now, let's redraw this and determine R and S at each center. And there's 2 here in this case. Okay, so here we have a bromine attached to, so we're looking at this center. It's bound to a bromine, a carbon, a hydrogen, and another carbon. So we don't have to continue at this point because bromine is higher priority than carbon because it has a higher atomic number. Then we have a carbon bound to 2 oxygens in our Cahn-Ingold-Prelog rules. It's double bound to an oxygen and then a hydrogen. And comparing that to this position, which is a carbon bound to a chlorine and another carbon. So this is where the additive idea isn't true because the atoms aren't the same. That's why I tried to be clear in the initial explanation with this molecule that we had. It's additive here because all the atoms are the same that we're comparing. But here we're comparing a carbon bound to a chlorine or a carbon bound to 2 oxygens. So it's that first point of difference, which is the chlorine. Chlorine is a higher atomic number than oxygen. So this whole group down is the second priority. And then the CHO is third. Okay, hopefully that makes sense. So now this looks like R because it's going clockwise. And the last thing to point out in all Fisher projections is the vertical lines are dashes and the horizontal are wedges. So if the hydrogen is on the dash or on the vertical, which is the dash, then the chirality is what it looks like. If it's on the horizontal, then it's the opposite of what it looks like. So here it looks like R, but the hydrogen is a wedge because it's on the horizontal. So it's actually R. Or sorry, it looks like R, so it's actually S. So it looks like R based on these rules, right? It's going clockwise, but the hydrogen is on the horizontal, which is a wedge here. So it's the hydrogen's like here. So because of that, you have to switch the configuration to the other direction. So this is actually S. I made a mistake in the first explanation, but hopefully I redeemed myself there and that makes sense. There's a lot of stuff going on here. Feel free to ask questions. Otherwise, I'm going to erase and do the other center because I'm out of room and I don't want to complicate this drawing more. Okay, I don't see any questions. All right, so we had this, which was S. 1, 2, 3, looks like R, hydrogen's on the horizontal, so S. Now we're looking at this center. So this center is a carbon, carbon, chlorine. So again, you don't need to go to the next bond. Oops. Don't need to go to the next bond yet because the chlorine has higher priority over the carbons. Now you do have to go to the next bond because it's carbon bound to a bromine or a carbon bound to an oxygen. So the carbon bound to the bromine has higher priority. So this is 2. This group then is 3. The hydrogen is 4. So this looks like R. By coincidence, all of mine that I've picked have looked like R, but it's going clockwise, so it looks like R. The hydrogen is in the horizontal, so it's actually S. So hopefully that makes sense. I don't want to waste the time writing it, but the hydrogen is on the horizontal, just like it was in the previous example. So it is the opposite of what it looks like. It looks like R, so it's actually S. So for as far as our determining enantiomers, stereoisomers, this is SS, and we'll have to compare that to what it looks like or what it is in this molecule. So now, again, any questions or anything? All right, so now if we compare this carbon, I'll redraw this because I wrote all the numbers to compare the structures. So here we have a carbon, carbon, and a bromine. So the bromine's highest priority. Then we have a carbon bound to a chlorine, so that's 2. And then the carbon bound to the oxygen is 3. This looks like S. The hydrogen is in the back, so it looks like S. And the hydrogen's in the back, so it is S. This position is S. Okay, and then once more to do the other center. So if we're looking at this carbon, the chlorine is highest priority, then the carbon bound to the bromine, then the carbon bound to the oxygen. This looks like S because it's going counterclockwise, and the hydrogen is in the front, so it's actually R. So this is SR if we were comparing it to this guy. So these are diastereomers because we have changed one chiral center, its absolute configuration, but not all of them. So if it was SSRR, that would be enantiomers. Because it's SSSR, that's diastereomer. Make sense? All right, we have about 20 more minutes, so I'll ask you guys if you want me to switch to Bronsted-Lowry and Lewis acid-base stuff, or if you want me to continue with at least one more example of this stereoisomeric stuff. Cool with either? Acid bases? Okay. We will switch. So let's start with Lewis acid and bases, because I think that the idea of Lewis acid bases is like all of organic reactions is function under the Lewis acid base idea. The Bronsted-Lowry acid and base is also useful, but you're usually showing the movement of electrons and not the movement of protons. So that's why this is better. So first of all, like I mentioned at the beginning, all of these are definitions of acids and bases. They all are applicable in their own context. So whenever you're solving a problem, you need to understand what context you're working under. And at the beginning here, it'll be explicit. They'll tell you like identify the Lewis acid and the Lewis base, but later in the course, it won't be explicit, and you'll need to infer based on the type of molecules that you have, which ones they want you to do. But regardless, with that, the hat that we're under now is Lewis acid and bases, which is movement of electrons is what you're interested in. So with that, then bases are electron donors. So they must have a lone pair or a negative charge or something like that. And then acids are electron acceptors. So they have like a positive charge, or they have an ability to take another bond. So for example, a base would be like Br minus, or anything with a negative charge like that. Anything with a lone pair, really. It doesn't have to have a negative charge. That would be one example. And then an acid could be anything, but let's say this carbocation, for example. Oops. There's a positive charge on that carbon, which I'm trying to draw it small, but anyway, there's the negative charge, positive charge, and that's driving these movement of electrons. So that's the general idea. And now you need to then be able to quickly identify, based on a set of molecules, a set of reactants, which is going to function as Lewis acid and Lewis base. And it's all based on these idea of, is there a lone pair, is there not? So let's look at an example here. I'll just use the same Lewis acid we talked about. Okay, so first the question is identify Lewis acid, Lewis base. Well, we know that this is a Lewis acid basically because we just said it, right? But if you also look on this definition, this has a positive charge. So that means that this carbon only has 3 bonds to each to these other carbons. So it could accept another bond, and it could accept that bond from a Lewis base like this molecule because there are lone pairs on this oxygen that can then be used to create the new bond. So here's our Lewis acid, Lewis base. Now this is the most important part of Lewis acid and Lewis bases, and why I decided to go with it first, is because in chemistry, and organic specifically, you want to explain how electrons move to create a new bond. So just like in resonance structures, where we show that this lone pair, this negative charge moves here and moves here, and then you create this new molecule, which is really just the same, but you've shown that this lone pair has moved here to create this bond, and then this bond breaks to put the negative charge, so put the lone pair on the oxygen that makes the negative charge. So just like this, you can use this arrow from that lone pair to the carbon and show that you're creating a bond with your Lewis base, your Lewis acid. So this lone pair creates the bond to this carbon that has the positive charge. So now this can be confusing for students, but you have to then show how these are bound. So I like to redraw it usually the way that they have it so far. So here I'm just redrawing this with the hydrogen down, just because I'm creating this bond to this carbon here. So here is the carbon that I created the bond to, right? So let me number this stuff. 1, 2, 3, 4, and that's it. I'll just do that. So 1, 2, here's 3 at oxygen, and then 4 is this carbon that's bound to then 3 methyl groups. And don't forget your positive charge from formal charge counting stuff. But this is why this point is so important, is in Lewis acids and Lewis base chemistry and most of organic chemistry, you're going from a lone pair or a negative charge to something that's positive or partial positive if there isn't a actual formal charge positive like there is in this case. So there may be a dipole or something that drives the reaction, but you can represent the formation of the bond by these curved arrows, which is like very important. So questions on that? We'll jump into one more example and then we'll talk about Bronsted-Lowry if you don't have questions. Okay, so now let's do a much different example just to illustrate this. So let's have CN minus plus this goes to whatever we're we're determining that. So this is a harder question. We're asked, first of all, Lewis acid, Lewis base. So right away, you would be inclined to say that this is a Lewis base because it's negative charge, right? Well, that's correct, but you have to know why. So you have this Lewis structure. So the negative charge is localized for our formal charge counting on the carbon. So that means that the bond that's going to be formed is between the carbon's lone pair and whatever it's binding to, not the nitrogen's lone pair. So this is the Lewis base part. This isn't. Just because this has the negative charge, the nitrogen is satisfied. It has its charge at 0, which is stable. So it has no reason to create a new bond. So it's not going to. Now, look at this guy. This is acetone. This has a lot of stuff going on. So this could be a Lewis base because of the lone pairs, right? So this oxygen could function as a Lewis base, and that's completely correct. But it won't in this case because we have a negative charge versus just a lone pair. So the negative charge is like a better Lewis base. So that means that this must be a Lewis acid. And now we have to explain why. So this is what I briefly mentioned. So here we have a difference in electronegativity between carbon and oxygen. Carbon is electropositive. It's not very electronegative compared to oxygen. So this would have a partial negative. This has a partial positive because there's the dipole going towards the oxygen. The dipole shows the movement of electrons. If this all isn't making any sense to you, there's a video on my YouTube channel that explains dipoles in much more detail, but I'm not going to spend the time to do it here, but check that out if this is confusing. But that once you understand that, you'll know that there's a difference here in the electronegativity and then ultimately the amount of electrons that are localized on a particular center. So here we know that this carbon is then electropositive, so this negative charge, the lone pair on the carbon, could attack the positive charge here because the partial positive charge, because this is negative, this is positive, it's the same electrostatic Coulombic interactions as driving all of this. So you have this going on. Now, this can't be the final answer, and there has to be another movement of electrons. And the reason is you're going to put too many bonds on the carbon. So let me draw what this would make just to explain this. So you have the double bond to the oxygen still, and then another bond to our carbon nitrogen, or CN. So this carbon now has 1, 2, 3, 4, 5 bonds, right? Can't have that. High carbons can't have 5 bonds. So this just simply won't happen. So you have to then consider where can these electrons go if you're creating this bond. And they can go onto the oxygen because we know that oxygen is electronegative. It's going to be attracted to, it's going to be able to hold the negative charge better because it's electronegative. It wants the electrons. So, so if I redraw this, what I'm insinuating is if you go here, you can then break this bond onto the oxygen. So now you're still creating the same bond that I show above. The reason this is different is because you've dumped the 5th bond, what would have been the 5th bond, onto the oxygen as a lone pair, making the negative charge there. So this is the correct answer to this question, to the Lewis acid-base chemistry for this example. So this example illustrates that there can be molecules like acetone that can function both as a Lewis acid or a Lewis base, and it will only be defined by the other molecule, like which one it will be. And in this case, this was a much better Lewis base, so that defines this is going to be a Lewis acid. If you had different chemicals, then it would be different. But I was going to show an example, but I don't think we really have the time. So are there questions on this? Because I want to use the last few minutes to talk about Bronsted-Lowry. We have 11 minutes left. All right. No questions. So again, acid and base stuff is always a definition. So it depends on how everything's defined for what you're looking for. So in the Bronsted-Lowry definition, you're interested in the movement of protons now, not the movement of electrons. So in reality, that's the movement of hydrogen atoms. But you'll always see it written as movement of protons, but it's just a hydrogen atom being moved. Now, so with that then, acids are proton donors or hydrogen donors, and acids then, or bases rather, are acceptors. Okay. So now let's look at an example. So like, let's see here. This is a common example. We're out of room. There we go. Okay. So if you look at this, it's these Bronsted-Lowry definitions are usually going to be equilibrium arrows. And a lot of stuff in organic is going to be equilibrium arrows. Do they usually make one or two products? I assume you're referring to Lewis acid-base stuff, which I didn't. I just saw your question. It depends. Most of the time, one products, if I had to pick, but it really just depends on what you have. It could make two. So here we have this proton is going to this hydrogen. If we compare what's happening here, so we have this going into this negative charge. So this is acetic acid that becomes acetate. It's lost the proton. So then this is the acid, the Bronsted-Lowry acid, because it's donated its proton. It's an acid from our definition above. This is then our Bronsted-Lowry base because it's accepted the proton from the acid. Now, these are the products. So in the Bronsted-Lowry definition, the products are always the conjugate of the reactant. So here, if this is the Bronsted-Lowry acid, this is its conjugate base because now it has lost the proton. So it has given up its proton to become a base. Now it could accept a proton. And then this is the conjugate acid because here we have our base. It's accepted the proton. Now it could donate it as the acid. Okay. Does that make sense? Identifying that? All right. So now, a hard question in the Bronsted-Lowry stuff is which direction is equilibrium lying? And that all has to do with the pKa values or your estimation of the pKa values. Sometimes you won't be given them. So in this case, I'll just give it to you just to make this first example a little bit easier. So the pKa of acetic acid is about 5. I don't know it offhand. It's 4 point something. There's some decimal, but it's about 5. And then the pKa of phenol, which is this thing, the benzene with the OH, is about 10, somewhere between 9 and 10. So pKa, first of all, this is really important to mention, pKa is a log scale. It's the negative log of a Ka, which is the equilibrium constant. So you don't need to know all the details of the math and on that. That's more of a analytical chemistry question, but you do need to understand that it's a log scale. And that means if something has a pKa of 5 compared to something that has a pKa of 6, that means that 5 is 10 times more acidic than 6.